We're now here in Unit 9.2 on linear regression. Now, in our discussion about correlation regression in the last unit, we asked two questions. Here they are. Number one, is there a relationship between the two variables? And secondly, if there is a relationship between them, how can we express it with an equation? How can we express it mathematically? So we answered the first question back in 9.1. Now we'll answer the second. This is a section on linear regression. So we need a little discussion about lines. Just remind ourselves of a few things about lines. So straight lines, number one, are determined by 2 points, x1, y1, and x2, y2. The subscripts just keep track of which value you have. First x, first y of the first point. Second x, second y of the second point. Straight lines cross the y-axis at some point, 0b, little picture here. The first component is 0 because on our picture here, our graph, here's 0 for the x. You're not to the left, you're not to the right. We're right on the y-axis, so the x is 0. And then some number of units, b, could be above or below. And third thing about straight lines is they have a certain steepness, which is measurable. And we call that steepness the slope, and we denote it with the letter b. So given a scatter diagram, we wish to determine the line of best fit. Now, a couple other names for this line. It's also called the line of regression of y on x, or just line of regression, or regression line, and the line of prediction for y, because we're going to predict values of y. This line, the regression line, will have this form right here. Y equals a plus bx. Now, that's just one way to write this. Sometimes it's written like this. All right, what we're used to back in the algebra course is this, right? Y equals mx plus b. That's what we're used to seeing, where m, that's the coefficient of x, that's the slope, and b, that constant out there by itself, that's the y-intercept. So matching things up here, the constant is this one right here, so that would be the y-intercept, and b, the coefficient of x, that's the slope. All right, so it's just a matter of changing names. Instead of mx plus b, we could write bx plus a, but we're going to write it as a plus bx. Now, I've also seen it like this, so just depending on who you're reading, I've also seen it like this, y equals b naught plus b1x. Just different ways of writing it. So we're going to construct this equation from our scatter diagram, and to construct it, we're going to use what's called the method of least squares, all right? The method of least squares. Here's where we're going with this. Here's a scatter diagram. Suppose this is our scatter diagram. Now, I've got kind of a linear relationship here, right? I mean, as the x's increase, the y's increase, and they all seem to be near some kind of a straight line. Well, it's that straight line that we're looking for. Now, what I would like to do is somehow determine how to put a straight line in here so it's as close to every one of these points as I can get it. For example, if I put this straight line in here, it might go through a couple of those points, but then it would be off by quite a bit for these other points. And then if I put it over here, well, it's closer to some points, but now farther from others. So the problem is, how do I get this line in here and as close to every one of those points as possible? Well, once we get it, that's why we call it the line of best fit. So here's what we'll do. I'm going to draw a picture here in a minute. So let xy, let that be the actual point, and xy hat be the estimated point. Now here's what I mean. If I come back up to this picture up here at the top, all right, maybe I look at this point right here. All right, now that's the actual point. So in this case, what I would have is that point right there, that would be the xy. That's the actual point. However, if I draw this line, if I put that line, that's my line of best fit, I'm not really going through that point. I'm missing it. So I still have the right x value, right? I still have the correct x value, but the y value I'm missing. In this case, I'm too low. So that point right there, that would be the x, y hat. So in my relationship, when I put x in, what I really want is that y. That's the actual y. But when I develop my equation, I'm not going to get that one. I'm just going to get an estimate for it. I'm going to get this estimate y hat. And of course, I want to place the line, high above, below, what angle. I want it so that I get the closest y to this one. Now down here, here's my xy. That's the actual point. Here's the estimated point. This is just a magnified version of this up here. So what I do here is I'm making an error, right? When we do this, when I get y hat, I'm making an error because it's not really the value of y. So I'm making an error when I do this. And that distance right there, that's the error, all right? I'll just call it E. That's the error that I'm making when I approximate this point here, when I approximate this point with this one here. So our goal is this. We want to place the line, all right, put this line, what height, what angle, put that line in so that the length E, right, that length right there, is as small as possible for every point on our scatter diagram. Minimize this length for every point on our scatter diagram. So we want this distance right here. Now I'm calling it E here, but what is it actually? Well, it's actually y minus y hat. Y hat minus y, it doesn't matter. I'll just take y minus y hat, right? That distance. Y minus y hat. We want that to be small. In fact, I want every one of these to be small. So we want every one of these y minus y hats to be small. So if I got all of these small, so this distance is small, I have a bunch of these distances, so what if I added up all those distances? I want that to be as small as possible. Right? I got all these individual distances. Add them all up. I still want that to be a small number. So we want the sum of y minus y hats to be as small as possible. So remember what our line is going to look like. Our line is going to be this one right here. Y, now actually we use y hat because we just get an estimate. Y hat is equal to a plus bx. So our line, y hat, is completely determined by this a and b, right? Y hat is a plus bx, and if we know a and we know b, we've got the line. So here's the formulas for a and b. So let's look at them. We're not going to derive these. We're just going to use them, or actually they're programmed into our calculator. Our calculator will do all these computations for us. But what is b? Now, does that look familiar? Like if you go all the way back to the beginning of the course when we did standard deviations, it looks like there's a standard deviation in here. And then a itself is what? The average of the y's minus this number here, that this is the slope, remember, times the average of the x's. So remember our form here. Our form is this. Y hat equals a plus bx. So how do you get what is this b here? This is how you compute the slope. And how do you get the a? Well, the a, you need the slope. So we get b first, then a. Let's do this example using our calculator. We are going to have our calculator make all these computations for us. Otherwise, it's a really long process. So what do? You go to Stat, to Edit. Now, you may have numbers in there from the last time we did this. So if you want to clear those out, remember what to do. Bring your cursor over to L1, take it up, use your up arrow, get it on L1, press Clear, and Enter. That will clear all those entries. Then right arrow over to List 2, up arrow to L2, press Clear and Enter. That'll clear last. Now arrow back to List 1. And in List 1, type in these numbers. 1004, 975, 992, 935, 985, 932. Press Enter. Right arrow over to L2. Type in these numbers. 40, 100, 65, 145, 80, 150, press enter. Now you got your data in there. Go to Stat, right arrow over to Tests. Now you scroll down quite a ways. Scroll to item F. Now item F says Linear Regression T-Test. And what you come up with when you press enter from F, you end up with all this stuff here, all right? So what do we want for our X list? Our X list, this is the explanatory variable. We're going to put in L1, right? So you have to get L1. So what do? You press second and number 1, right? Second and 1. The regular number key 1. Press enter. Then it wants to know the Y list. Well, that's our response variable. That's coming from list 2. So press second and the number 2. Now frequency, just 1. Every one of those numbers appears just once. Now beta and rho, we're not doing anything with beta, but we are doing something with rho. And what we're testing is this. So it's a t-test. So maybe I'll write it over here. Here's our null hypothesis, our alternate hypothesis. Our alternate hypothesis is that rho, the coefficient of correlation, now we could just say that it is not 0, or if you remember the scatter diagram looked like this. Right, so it looked like we had a negative correlation, or we could say that rho is less than 0. Just so we're all on the same page, why don't we just go with this one right now? That's what we're testing. So let's just say that this is not equal. So we'll say not equal to 0. Regression equation, we can just leave that blank. Now go down to calculate. Now when you press enter, a lot of information comes up. First of all, they're telling us the form of our equation and what we're testing. We're testing that rho is not 0, that there is some correlation, right? If this is 0, that means there's no correlation. We're testing that it's not 0. So we're testing that there is some correlation. Actually, back over here in our hypothesis test then, we would probably write what's the opposite of not 0? Rho equals 0, that there is no correlation. All right, so we're testing that there is some kind of a correlation here. Then we get a t-value. Now, if we had done this hypothesis test with the critical region approach, that's what we would want to look at, but we're doing it with a p-value. There's our p-value. But we know how to read this, right? This number here really is what? 1.57 times 10 to the negative 4. And to get this number into scientific notation, that's a negative. We must have moved that decimal point 4 places to the right because of the negative. So to get it out, we'll go 4 to the left. So here's our p-value. 4 to the left, I need 3 zeros, 0, 0, 0, 1, 1, 5. Or if I round that off, I'll just say this. P is equal to 0.0002. There's our p-value. Now it's also giving us, right, what does it also give? It also gives us A and B, right? So we could actually write the equation. Here's the equation right here. So let's go ahead and write that equation. So I'll do it right here. Y equals A plus BX tells us that Y, I'll write Y hat equals A. Now the A value is that 1496.78 plus BX. Well, B is negative, so negative 1.44x. There's our equation. Here's the question, though. Is it any good? Does it give us a good approximation or not? That's where we're going to use our values of P to determine if we have a correlation or not. Let's look at our hypothesis test. The claim is actually that there is a correlation, right? That rho is not 0. There is a correlation. If rho is 0, there's no correlation. So we're testing this one here in a sense. We want to know if we can nullify this, the null hypothesis. Can we nullify this? Can we say that this is not true? Let's look at our hypothesis test. We're really testing this claim right here, that there is a correlation, right? That rho, the correlation coefficient, is not 0. So if it's not 0, that means there is a correlation. Rho being 0 says there's no correlation. We got a p-value of 0.002. Now, what does that mean for us? Okay, I'm thinking that 0.002, well, here's rho and alpha. Okay, choose an alpha, 0.0002. What if we even choose 0.01 or 0.05? It doesn't much matter because 0002 is less than 0.01 or 0.05. All right, so I got a less than. Less than reminds me of small. We're dealing with p-values, so I have a small probability, but I'm actually seeing this. So if it's a small probability, but I'm seeing this, I think I'm seeing something that if H naught is true, this is unlikely. But I don't think I see unlikely things, so I'm going to reject H naught. All right, this is just how I remember it. If you can remember it here, if you get a less than, you can reject. If it's greater than, you fail to reject. So if I write up the conclusion, I would say at alpha equals 0.01, this sample indicates there is enough evidence to conclude that well, what are we doing? We're rejecting this in favor of this. This says that there is a correlation. So I'm going to say there's enough evidence to conclude that there is a correlation between X and Y. Okay, well, that's good. So now we conclude that there is a correlation. So what does that mean? Well, down here at the bottom, right? Down here at the bottom, we got an equation. So is it good or is it not good? So we're concluding that there is a correlation. So this means that this regression equation is a useful equation, is a useful predictor for Y. Given an X, I can predict Y with some kind of accuracy. So then there's another question here is, how accurate is this? Are we getting a really strong, good estimate or kind of a weak estimate, but okay? Let's answer that in the next section.